All right, we'll get started today. So we're gonna begin chapter 5 today. If you're keeping track along with the book, so we're getting, believe it or not, close to the halfway point in terms of covering material for this course. So the topics today are going to take a pretty significant shift in direction. So the textbook we use is called Atoms First, which means we cover things at a very high level of detail, and initially that deal with individual atoms and molecules, the nucleus, the arrangement of the electrons around them, the way that those electrons are shared when we make bonds, and then more recently the structure and bonding in covalent compounds. So everything at sort of the individual atom and molecule level. What we're transitioning into now is going to start talking about the physical and chemical properties of collections, large collections of atoms and molecules, how we measure them, how we quantify them, and a bit about how they react with one another. So it's, again, a pretty significant shift in approach, and you'll see that it's a lot more quantitative in terms of the typical questions that we ask you. I think I always thought this part of chemistry was pretty fun. You and I don't always have the same definition of fun, obviously, but I do think it's more straightforward. It's not necessarily easier, but it's a little bit more clear cut in terms of the expectations and the kinds of things they'll be doing. And the math itself is not that difficult, as you'll see. It's primarily multiplication and division. Dimensional analysis, kind of the type that we covered early on, comes into play here. So it's not really complex math. It's just being able to internalize all the necessary relationships and the sequence of steps that are needed sometimes to get through what are often multi-step problems is the challenge. All right, but we're going to start at the very basic level today with defining some terms. The first one being atomic mass. So in atomic mass, we're talking about, as the name implies, the mass of an atom, or as we'll see later on, that's more often expressed as the mass of a large collection of those atoms in an element. But it can be sort of formulated in a couple different ways. But one of those is to actually talk about the mass of an individual atom, which is related to the mass number that we covered before, but as we'll see, not exactly the same. And so the unit that we can use is called the AMU, atomic mass unit, which essentially is a convenient way of expressing the mass of an individual atom at a not too tiny level. Because if we were to use grams or kilograms for the masses of atoms, all the numbers would be on the order of like 10 to the minus 24, or 10 to the minus 27, depending on what units you're using. And that's just not a practical way to do things. So we define the AMU as a more convenient measure of mass when we're talking about atomic masses. And what it's defined as is the mass of the carbon-12 isotope. So carbon-12 would have 6 protons and 6 neutrons. It's a particularly abundant one. So it's the mass of that divided by 12. So as we said, it is closely related to mass number. And so with this definition, the atomic mass of carbon-12 is exactly 12. But the reality is, we'll see later on in the next slide, is that the masses of all the other isotopes typically are not equal to the mass number. They're closely related to that, but they're not exactly the same for reasons we'll get to. But we use carbon-12 as the standard. So basically, all atomic masses are measured relative to this isotope, to carbon-12. And so we're not going to get into the experimental details, but there are techniques available, one of them called mass spectrometry, that pretty easily allows you to measure the relative masses of two things, but not necessarily in the absolute terms. So you kind of set one of them as the standard, which was chosen to be carbon-12. You measure the mass of everything else relative to that, and then using the same scale, you can then report their atomic mass in AMU. So as an example, if we just go to the other most prominent isotope of carbon, which is carbon-13, not as abundant as carbon-12, but still about 1% or so abundant. The mass of carbon-13 divided by the mass of carbon-12, this is an experimental number. So again, these experiments that people do can give you these sort of ratios or relative masses. It comes out to 1.0836. And so then if we want to state the mass of carbon-13 in AMU, we just multiply this number times 12 AMU, which is the mass that was set for carbon-12. So carbon-12, again, I'll just write that out here if that wasn't clear. The mass of carbon-12 is set to be exactly 12 AMU. And so using this ratio, the mass of carbon-13 would just be 13.0032 AMU. Now you notice, though, it's not exactly 13. It's not exactly equal to the mass number, which is 13. So the question is, why is it a little bit different? And that comes from something we're not going to talk a lot about, but just to give it as appropriate background, it's not exactly equal to the mass number, except for carbon-12, where that's sort of set as to be the case, because of this relationship that Einstein came up with, E equals mc squared, which states that energy and mass are sort of interchangeable with each other at some level. And what happens is that when a nucleus forms, a lot of energy is released when the protons and neutrons come together. And since E equals mc squared, since energy and mass are related to each other, that changes the mass of the nucleus depending on how many protons and neutrons it has in it. All right, and so again, you don't need to worry about that explanation too much, but you should be aware that the mass number, which is a whole number, sum of protons and neutrons, while close to the atomic mass for most isotopes, is not going to be identical to that because of E equals mc squared. Now, the other parameter that we need to really define the atomic mass of an element is the percent abundance, because most elements on the periodic table, carbon being one example that we've talked about today, they're not just a single isotope. They're going to be a combination of multiple isotopes that make up their sort of natural composition. And so if we want to define the atomic mass of that element, which is a mixture of isotopes, we need to consider not only the masses of the isotopes, but how abundant each of them is. So percent abundance is the relative amount of each isotope in a natural sample of the element. Now, I suppose it's possible that these percentages could be different on some other planets than Earth, but here on planet Earth, that's how everything's defined, of course. And each element is going to have a certain distribution of isotopes. Now, there are some elements where a single isotope makes up effectively 100% of that element. That's not impossible, but most elements, as we said, have a mixture of isotopes involved. So going to the example of carbon that we've been dealing with today, the most abundant isotope of carbon, as we said, is carbon-12. And so in a sample of carbon, 98.89% of the atoms would be carbon-12, which is 6 protons, 6 neutrons in the nucleus, but that leaves another 1% or so for carbon-13. Also a very tiny amount of carbon-14, which is radioactive, but these are the two that make up effectively 100% of the mass. So if you had a sample of carbon just sitting here on the table, 98.89% of those atoms would be C12 and 1.11% of them would be C13. So then when you're defining the atomic mass of carbon, you need to consider that both isotopes are present and that they're present in different amounts. So the atomic mass of an element, not an individual isotope, would be a weighted average of all the isotope masses. I'll double check that I'm not muting myself today. I think we figured that out. All right, so weighted average of all isotope masses, which is going to be the fractional abundance of the first isotope multiplied by its mass. So fractional abundance is just the percent divided by 100, so the relative amount out of 1, plus the fractional abundance of the second isotope times its mass, and so on for however many isotopes you have. So, you're not limited to 2. Carbon has basically 2, but there could be more than 2. But that's how the atomic mass of any element would be defined, as a weighted average of all the different isotopes that are present, where you take the fractional abundance of each isotope multiplied by the mass of that isotope, and then add them all together for however many there are. Okay? So if you go to, and we'll get to this more in detail later on, but this would be the number that's found on the periodic table as the atomic mass for that element. So when you look at the periodic table, I'll just give that away here now. We'll talk about this more later when we start using these. We haven't talked about this a lot yet, but each element on the periodic table has a number below it. So the number above is the atomic number, the number of protons in the nucleus. The number below is the atomic mass, which is that exact number that we just defined, the weighted average of all of the isotope masses in AMU. Okay. So let's give an example of how we use this relationship. A couple different ways we can ask you about this. So one would be we just give you masses in the abundances and ask you to determine the atomic mass. And so that's just using that exact equation I just gave you, where you take the weighted average of all the isotopes. So we need the fractional abundance of the first isotope. So boron has two isotopes, boron 10 and boron 11. So the fraction of that isotope multiplied by its mass. And then add that to the fractional abundance of, I should say fraction, not fractional, of the second isotope multiplied by its mass. So again, only two isotopes to consider here, so that makes the math a little bit more straightforward. Now, again, the only difference is that we're typically going to report those abundances as percentages, which is the number out of 100. But for this equation, you need the fractional abundance, which is the percent divided by 100. So the fractional abundance of the boron 10 isotope, we're giving it to you as 19.90%, but we have to take that number and divide it by 100 to get it to the correct form for this equation. So 1990. And then the fraction of boron 11 again would just be that number, 80.10% divided by 100, which is 0.80180. So there are going to be some situations starting here and some other things that we do in the near future where you have to consider the possibility of either percent abundances or fractional abundances. And so just remember that they're related by a factor of 100 and make sure you use the correct one. And then finally, to answer the problem as stated, we just have to calculate the atomic mass by putting the numbers in. So the fractional abundance of the first isotope we said was 0.1990, and its mass is 10.01294 AMU. So again, not exactly equal to the mass number, but close. And then the fractional abundance of the second one is 0.8010 times the second isotope mass, which is 11.00931 AMU, the mass of boron 11. So numerically, that comes out to 1.993 plus 8.818. 10.811 AMU would be the weighted average atomic mass of naturally occurring boron. Okay. So that's how that works out. It's just multiplication and addition, not too difficult from a math standpoint. Just a couple of things to keep in mind. We'll do one other example on the next page that involves some algebra. But if you're using this relationship, again, don't forget to convert percentages to fractions. Otherwise, you get a number that's 100 times too big. One other thing that's relevant too is if you look at your answer, it should be somewhere in between the extremes of the isotope masses that are present. So if your lightest isotope is 10.01 and your heaviest isotope is 11.01, your atomic mass better be somewhere in between those two. Can't be outside of that range. And one other thing that sometimes comes up, we may, in a less precise situation, we might just give you the mass number. We might just give you boron 10, boron 11, but not provide the individual isotope masses. In that case, you would have no choice but to assume that the mass of boron 10 is 10 AMU and the mass of boron 11 is 11 AMU, which is not exact, but in many cases close enough. So just be aware there's some slight variations that can come up, but it's really this relationship that dictates all of it. But then the other way that we can present this information is by actually asking you to solve for the abundances, not give them to you, but have that be your unknown. So here we're talking about the element chlorine, and this is the atomic mass that you would find on the periodic table for chlorine, 35.45. And it has two naturally occurring isotopes where we're giving you their mass number and their masses. But we want to know what is the percentage of the 35Cl isotope. So in this situation, we have two unknowns because we don't know the abundance of either element. or sorry, of either isotope. We need to find one of them, but we don't know either of them. So whenever you have two equations, as you know from previous math classes, that whenever you have two unknowns, you need two equations. So we're gonna be able to solve for either or both of those. And we're gonna, just to make things simple, we're gonna call the fractional abundance of the 35 isotope, which is what we're looking for. We're gonna call that X. And then the second unknown, which is the fractional abundance of the other one. And we won't go higher than two unknowns in problems like these. It's not really easily possible to in most cases. Anyway, so two unknowns is probably the highest we would go. Math gets pretty tricky after that. So we have two unknowns. We need two equations. So the first of those that we can consider is just the definition of atomic mass that we've been covering, which is that the atomic mass of chlorine, which is 35.45, is equal to the weighted average of the isotope masses, which is the first isotope mass, 34.96885, multiplied by the fractional abundance of that isotope, which we've defined as X. So that's our first equation. It's just based on the individual isotope masses multiplied by their fractions, which are the unknowns, X and Y. The second isotope has a mass of 36.96590 and an abundance of Y. So that's our first equation there, which again, this is atomic mass. This is the isotope masses multiplied by the unknown abundances. The second relationship is that whenever we have a naturally occurring element with different abundances for the isotopes, the sum of all the different abundances has to equal 1 or 100%. This time there's only two of them to worry about. So that means the sum of these two fractional abundances, X and Y, must equal 1, where the percent abundances would have to be equal to 100% if we added those together. So that's true whether you have 2, 3, 4, however many different isotopes you have, the sum of all of those fractional abundances would equal 1. So what we can do then is rearrange this and say that we're solving for X, so we want to get rid of Y. So Y is equal to 1 minus X. We're going to take that and put it in here for Y, okay? So we just rewrite it with the first term unchanged. Second term, we're going to put in 1 minus X in place of Y. And then what I will sometimes do to save time in class, but make sure you're clear on how to do this yourself, I'll skip the algebra. So I'll put it into the magic algebra machine, which you don't have access to, unfortunately, on tests. And what we get is X is 0.7590. We asked for the percent abundance, so you have to multiply that by 100 to get 75.90%. All right, so again, mixing up abundances in terms of fractional abundance or percent is a common mistake, so be clear on that. But again, here we're just sort of working backwards. We didn't give you the abundances, but with a series of two straightforward equations and some substitutions, we could get to it. So that's really, in terms of this relationship that we're starting with today, that's about all the variation you would have. You know, you're going to either calculate atomic masses like we introduced, or you're going to solve for an unknown using the same relationship, which we did here. So there's not a lot more to that. Any questions on that concept so far? Now, the next thing that this leads us to, which is critically important for this chapter and the next three after it, is this concept of the mole, which is basically the standard way by which we measure amounts of chemical substances. And a lot of what we're going to be doing in chapters 5, 6, 7, and 8 is covering different relationships between some measured amount of substance that we're going to, that we could in principle measure in a lab, mass or other properties like that. We'll start with mass today. And then how that relates to how many moles of that substance we have, which is, again, sort of the standard uniform way by which we quantify chemical substances that are either involved in chemical reactions, or often when we're measuring their physical properties too, we do it in terms of moles. So first we have to introduce what a mole is. It's not the animal that I'm showing here, even though they're spelled the same. It is a counting word. So we have some of these in the English language. The one you're probably most familiar with is dozen. So if you have a dozen of something, that's 12. And if you have a gross of something, not as common, but maybe you've seen it before, that would be 12 dozen, or 144. So if you have a dozen eggs, that'd be 12 eggs. If you have a large family, you can buy a gross of eggs, that's 144. And then really old school now, but score means 20 of something. So the famous Gettysburg Address, 407 years ago, that meant 87 years ago, 4 times 20 plus 7. So those are counting words where, it's a stated word that tells you how many of something you have. And mole is exactly the same. It's a counting word that tells you how many things you have in 1 mole of that material. Now the number that's associated with the mole is quite large, 6.022 times 10 to the 23rd things in 1 mole. So it's an impractically large number for counting everyday objects, as we'll see on the next slide. But when we're counting exceptionally tiny things like atoms and molecules, it's very useful because, as we'll see, it's related to the mass of that substance and the atomic mass in particular that we've been covering. This number here is called Avogadro's number. I think it was a lecture that I ended up having to miss for some reason because of, I think, a family illness or something. But early in the semester, we covered Avogadro's I forget if it was the weather day or the day that I was out for some other reason, but we covered this in a recorded lecture anyway. We didn't cover Avogadro's number. We covered Avogadro, the scientist. Now, my understanding is that Avogadro, the scientist, had the important contribution that we covered earlier, which is basically the relationship between the volume of a gas and how many particles are in that gas, which is called Avogadro. And we'll talk about that in more detail later. I don't think he actually came up with Avogadro's number. The story that I heard, I should probably verify this is true because it's just folklore at this point, but someone else came up with this number, or some collection of people, but they had a huge man crush on Avogadro and just decided to name the number after him, even though he didn't come up with it. So it wasn't actually his discovery, but it's named after him. And that's the number that's referring to how many things are in 1 mole, which, as we'll see later on, things usually means atoms or molecules in the context of chemistry. But let's see what happens if we use Avogadro's number, or the concept of a mole, to count things that are a little bit larger in size. All right, so this is just like an order of magnitude problem. I'm not going to go through all the math in detail, but let's say that we are going to have, let's say we had 1 mole of M&Ms, and we were going to cover the entire United States with those M&Ms. Now, does anybody want to guess how many layers of M&Ms, how many layers would that be? If we cover the entire United States with 1 mole of M&Ms, and then we got done and we had to stack another layer on top of that, how many layers would we get to before we got to that 1 mole of M&Ms being run out of? Anybody want to, there's no right or wrong answer here. Yeah. 200. Okay, that's solid. Good guess. We'll see how close you are. I appreciate you putting your neck out there. So let's see what happens. Now, again, I'm going to give you some of the inputs. I'm not going to do the calculation, but if you wanted to try to do the calculation yourself, go ahead. It's not going to be something we'll have you on a test or anything, obviously. So let's just make some assumptions here that the volume of 1 M&M, these are all approximate, but it'll get us to the right idea, is 1 cubic centimeter. Okay. The area of the United States of America is 3.02 times 10 to the 6th square miles. So basically, you'd have to convert that to square centimeters and then figure out, okay, if I cover this with 1 layer of M&Ms and let's say they're 1 centimeter tall, how many M&Ms is that? And so you again, the calculation, I'm going to skip the details on, but that's the inputs to it. What you would come up with if you were to work out the math, which I'm not going to do for you, the height of the layers, the stack of M&Ms that you would use to cover the United States is 50 miles tall, which is 8 million layers. So your guess of 200 was a little bit off, I have to say, but not a bad starting guess. So it would require 8 million layers of M&M. You'd have to stack the M&Ms 8 million times to reach a mole over the entire United States of America. So just, again, an unfathomably large amount of number. Another one that's fun to think about is how many teaspoons of water are there in all of the oceans in the world? So the entire world is like, what, 75% water is what they tell you in grade school. I don't know if that number is exactly accurate, but it's probably close. And anyway, the volume of all the oceans in the world is around 1.3 times 10 to the 9th cubic kilometers. So if you convert that to teaspoons, a unit of measure that we commonly use in the US for measuring liquids, it comes out to 2.65 times 10 to the 23rd teaspoons, which is close to 1 mole. So basically, there's 1 mole of teaspoons of water in the entire world. So if you were to take out spoonfuls of water from the ocean until it was empty from all over the world, you'd have to do that Avogadro's number times before you got all the water out. So again, just telling you how absolutely gigantic that number is. So we don't use it to measure everyday objects like M&Ms in water. We use it to measure things at the atomic or molecular scale. So that's what the mole is. It's a counting number, but it's really not practical, even in a chemistry lab, to count out individual atoms and molecules. Now that relationship is going to be important, but we're not going to go in the lab and say, okay, give me 1 mole of water and start counting 6.02 times 10 to the 23rd molecules of water right now. Go do it. Like that would take you the rest of eternity. But there are other physical quantities that we have that are related to the mole. And that's what we're going to be, again, covering a lot of in this next couple chapters. So the atomic mass is one of those. We gave it in AMUs, which is sort of a convenient way of expressing the mass of an individual atom. But in an alternative, and in most cases more useful formulation for atomic mass, same exact number, but just alternative formulation of the unit, is that the atomic mass represents the mass in grams of 1 mole of an element. So we did the problem earlier where we had the atomic mass of boron was 10.81 AMU. Another way of thinking about that is that it's 10.81 grams per mole, meaning 1 mole of boron has a mass of 10.81 grams. Measuring masses in grams is something that we can very easily do in a chemistry lab, and you probably have before if you're taking the lab course. So that relationship is probably the most commonly used in chemistry, relating mass to moles of substance. So at this point, with the definition of a mole and with what I just told you, we now have 2 unit conversion factors that involve moles, because a lot of what we're going to do in the next, especially chapters 5 and 6, but to some extent, even the 2 after that, is going to be unit conversions involving moles, converting moles of substance into something else. And we're going to have not too many, but probably a collection of 4 or 5 different relationships that you're going to have to know how to use. And the first 2 are now given to you. So the first one is that there are 6.022 times 10 to the 23rd atoms or molecules, or more generally things, as we said, it can be used to count anything, even though it's typically used for atoms and molecules, in 1 mole of that substance. And then the atomic mass of the element in grams represents 1 mole of that substance as well. So those are 2 conversion factors involving moles that we have now. Sometimes a little bit of a point of confusion is, well, how do I know if Avogadro's number refers to atoms or molecules? Well, that's just a function of what that substance is made of. So if you have an element like carbon or boron, like we've talked about today, then there'd be 6.02 times 10 to the 23rd atoms of that element in 1 mole, because elements are made up of atoms, just a single type of atom. If you have a compound that's made out of molecules like water, H2O, there would be 6.02 times 10 to the 23rd molecules of water in 1 mole, because that's what water is made of, is molecules that have the formula H2O. So that's something that, we'll work through that in more detail as we go through this chapter, but something that's, we need to be aware of as we start it, that this can represent different entities depending on what that substance is made out of. But typically, as I said, it'll be atoms if you're talking about an element, molecules if you're talking about a compound. All right. So what that leads to is a lot of what we do in the first part of chapter 5 is just dimensional analysis type problems involving moles, and different combinations of these relationships, different ways of stating it, but really all centered around these 2 relationships: the definition of the mole and atomic mass stated as grams per mole. So let's go and just do a bunch of these, okay? Just to see the different variations we can have. So let's say we have a helium cylinder, which has much more valuable uses than filling balloons, although that's what it's often used for. So helium cylinder contains 239 moles of helium. How many helium atoms are in there? So this is a simple 1-step conversion, because what we're looking for is the number of helium atoms. So we're going to set up these problems the same way we did at the beginning when I first introduced dimensional analysis. Write out what you're looking for. Sometimes you can get there in 1 step, sometimes it's multiple steps, but you want to know, like, what quantity am I searching for? And then you start the problem with some quantity that you're given, which in this case is 239 moles of helium. And then you just have to think, is there a relationship between that quantity, which I'm given, and what I'm looking for? And in this case, there is, because the relationship between the number of atoms and the number of moles is just Avogadro's number. So we can do it in one step. We can cancel out moles of helium on the bottom, and there'd be Avogadro's number helium atoms in 1 mole. So 1 mole of helium would have 6.02 times 10 to the 23rd helium atoms. And so in one step, we can figure out that 239 moles corresponds to 1.44 times 10 to the 26th. As I already said, it's not usually practical to talk about how many atoms are in something in this way, but from the standpoint of learning what a mole is and defining it, we're going to, of course, expect you to know that early on. So just as a sort of summary of this relationship and how we know when to use it, if the problem asks you to count individual atoms or molecules, in other words, if it says how many atoms are in this sample, how many molecules are in this sample, that's when you're going to want to use Avogadro's number. So sometimes the trick to some of these problems is to look at the information you're given and kind of figure out quickly what relationship is even valid here. Because as I said, we're going to build up a collection of these relationships. And you have to know which ones you use and which time. So if the problem asks you how many atoms or molecules are in something, or if it states how many atoms or molecules are in something, then you're going to kind of want to be aware that Avogadro's number is going to be involved. And when you're doing that, the identity of the substance in that case doesn't matter. Avogadro's number applies to any substance. It's not dependent on what it is. So even though we told you here that it was helium, that didn't really matter. We would have approached the problem the same way if we asked for how many atoms were in 239 moles of any other element as well, whether it be carbon, boron, gold, whatever. So Avogadro's number is a uniform constant that applies to any substance. Doesn't matter what substance that is. Now, in other situations, though, the identity of the substance is important, and that's going to come into play when we're using the mass to mole relationship like we would here. Because if you're relating grams to moles, each element is going to have its own atomic mass that you would have to consider, which tells you how many grams that element are in 1 mole. And that's different for every element on the periodic table. So in that case, you do have to know what it is, and you have to use the correct number. So if any of you are, if any of you invest in gold, I don't, but I like the element from a chemistry standpoint. You might be familiar with the American Gold Eagle bullion coins. Those contain 31.1 grams of pure gold. And how many moles of gold would be then in that coin? All right, so again, we write out what we're looking for, which is moles of gold, which has the symbol AU. And we start with what we're given, which is 31.1 grams. And again, if you're relating grams to moles, we should immediately think about atomic mass. Does that? And again, there's sometimes confusion that you should, oh, do I divide or do I multiply by atomic mass? Well, in this case, we want grams to cancel. So we want grams in the denominator. We want moles in the numerator. So we're actually going to end up dividing by the atomic mass, which says that there's 1 mole of gold in how many grams? Well, for that, we have to look it up in the periodic table. So if you're not given what the atomic mass is, you have to go find it on the periodic table, but you'll always have that available. So let's zoom in a little bit on gold so we can see it better. All right, so there's gold right there, AU, and the atomic mass is 196.97, which again could be stated as AMU or grams per mole. So we're going to have 196.97 grams of gold in one mole. That goes in the denominator such that grams cancel out. And then again, in a one-step sequence, we can get to the number we're looking for, 0.158 moles. All right. So again, in contrast to the last one we did, as stated at the beginning of this, if you're converting between mass and moles, or vice versa, whichever direction you're going, you do need to know the identity of the substance and make sure you're using the correct atomic mass, because that's different for every element on the periodic table. All right. So that's the key difference here. The fact that it was gold was important in this problem because that specifies the atomic mass we should use. So those are simple one-step conversions, but we should be aware, as often as the case in chemistry, that sometimes you have to go to more than one step and kind of piece together small information. So this is not so recent anymore because I made this problem a long time ago, but this is from someone I knew back in graduate school who did this work. And they discovered that there's a nanoparticle that has a 1.3 nanometer diameter and it has 37 indium atoms in the structure. What is the mass of indium in one of these particles? So sometimes in problems, we give you unnecessary information, and just right off the bat, I'll tell you that the diameter of the particle doesn't matter. We don't have any relationships right now that relate number of atoms, mass, moles, or anything like that that relates to the size. So we're gonna leave that part is just extraneous information, but we're gonna use the number of indium atoms in the structure to figure out what the mass would be. So again, write out what we're looking for, which is the mass of indium. And we're told that there's 37 indium atoms present. Now, in this case, we have to think, is there a one-step process that we can use to get there? Let me move this down so I don't have to put it on a second line. The picture there. I'll sometimes have to do problems on 2 lines. I hope that doesn't cause confusion because the slide's only so wide and I can't write too small, but we'll start this one here if you should have enough room to do it in 1 line. All right, so the mass of indium is what we're looking for. We're told that there's 37 indium atoms in this structure. We want it in grams. Okay, so we're looking for the mass in grams. Maybe helpful to include the unit there too to remind yourself. All right, so the question is there a one-step calculation that tells us how many grams are in a certain number of atoms? And the answer right now would be no. So we could get the mass in AMU, but that's not what we're asking for here. We're asking for the mass in grams. So this is going to be a 2-step problem. We're telling you the number of atoms, so your mind should immediately think of Avogadro's number. So we can use Avogadro's number to figure out how many moles that corresponds to. And then in the second step, once we know how many moles there are, we can use atomic mass to convert that to grams. This is sort of our first example of a 2-step problem. So if we have 37 indium atoms, the first thing we're going to do is convert to moles. Something that I'll say over and over again in this section of the course is, when in doubt, convert to moles. I mean, sometimes it's not always obvious how you start a problem, or sometimes it's not always obvious where's this going to end up. But if you're at all stuck, the first thing you should think about doing in most cases is converting into moles, because that's almost always going to be involved. So we're going to convert to moles by using Avogadro's number. 6.02 times 10 to the 23rd indium atoms in 1 mole. Now that we have moles of indium, we can use its atomic mass. So we want moles to cancel and convert into grams. That's going to be the atomic mass relationship, grams per mole, which again, we have to look up on the periodic table. I'm going to give it to you here. IN is over here, number 49, and the atomic mass is 114.82. So that's how many grams are in 1 mole. So we have 114.82 grams of indium and 1 mole of indium. So moles cancels out. And now we're in the unit that we want, which is grams. So we stop there. And we multiply this and divide, and we get 7.05 times 10 to the minus 21st grams. So a very small number because we're only talking about 37 indium atoms, which is a rather small collection. So a very small number that we get as a result. But again, it's a 2-step problem this time. But the intermediate step is almost always going to involve moles. So figure out what you're starting with, figure out how to convert that to moles, and then typically from there, you can go forward with one of the other relationships that we have. All right, so any questions so far? All right, I think just one more that's sort of a 2-step problem like this, just to close this out. So we have now back to our favorite element, or one of my favorite elements, gold, maybe not yours, but a gold bar weighs, there's a typo there, weighs 12.4 kilograms. How many gold atoms are present in one of these gold bars? All right, so we have to start with what we're looking for, which is the number of gold atoms. What we're given is 12.4 kilograms of gold. That's the quantity that we know. And we're looking for the number of atoms. So again, if you're looking for how many atoms there are, you should immediately think that Avogadro's number is going to be involved, but we don't have a one-step relationship that relates mass to Avogadro's number. So we have to go, again, through intermediate steps. First thing we should do is convert to moles, as we said, is typically the case. Now, this is in kilograms, and atomic masses, we have to remember, are always in grams per mole. So if we want to use atomic mass to convert this into moles, we have to convert to grams first. Most of the time, we'll just giving you things in grams, but if it's in a different unit, you need to convert. So 1 gram of gold and kilograms of gold to cancel out. So there's 1,000 grams, 10 to the third grams, and 1 kilogram. Now we can convert that into moles. We saw earlier that the atomic mass of gold is 196.97. We got that off the periodic table. So we want grams to cancel, and we'll get to moles that way. So we want to put the atomic mass in the denominator, which is the mass in 1 mole in the correct units of grams. And then finally, once we're in moles, if we're looking for how many atoms there are, we should immediately think of Avogadro's number. So we want moles to cancel. Let's go down to the second line here. Moles will cancel out. And then Avogadro's number says that there's 6.02 times 10 to the 23rd gold atoms in 1 mole. So moles cancel. That gives us the number of gold atoms that we have, which is our stopping point. And for this part, you'll still need to know how to do exponents on your calculator when you're using Avogadro's numbers to make sure you're clear on that. 3.79 times 10 to the 25th atoms. Okay. So 2-step sequence using now both of the relationships, moles per grams, and then the definition of a mole, which is Avogadro's number. All right, so that's just mole conversion so far. There's of course more to come. So again, I'll pause one more time for questions on that stuff before we move on. All right, now the next thing that we're going to cover is very closely related to that. So we just showed that there's this very convenient relationship for elements that the mass in grams of that element per mole is the atomic mass. The atomic mass tells you how many grams of an element are in 1 mole. We have a very analogous relationship for any chemical compound as well. So we're not going to just be doing things with elements. We're going to be doing a lot of calculations, a lot of problems that involve chemical compounds as well. And so for that, we need the more general term, which is called molar mass, which, as the name suggests, is the mass of 1 mole of a compound. I guess more generally, we could say it's the mass of 1 mole of a substance. Units, again, grams per mole. Now, just to avoid confusion, for elements, the molar mass is the atomic mass. You can use those interchangeably when they mean the same thing. So there's nothing new here when it comes to elements, but we have to talk about how do we define this or how do we calculate this for compounds. It's relatively straightforward, but we'll get to it here in a second. There are some synonyms for this that you should be aware of just to not be tripped up on terminology. So molar mass is probably the most general and most precise, but sometimes it'll be called molecular weight. Or sometimes if it's not a molecular compound, but like an ionic compound, which is made up of, like you might see it referred to as the formula mass or the formula weight. They all effectively mean the same thing, and they're certainly determined the same way. There's some abbreviations for this. I think the most common abbreviation you would see in this course is MW for molecular weight. There's some old school sources, but I don't think we would use this anymore in this class that use this, like, I can't even draw it very well. This like fancy script capital M for molar mass. That used to be how we do it when I first started teaching, but that was ages ago. So do a little bit better than that. But you don't have to worry about that. But if you see that anywhere, if it's like a fancy script M, I'll just write that script M because I can't draw it very well. That can mean molar mass as well, but you'll probably see just MW is the most standard abbreviation. But any of these terms, molar mass, molecular weight, formula mass, they all can be used and they all effectively mean the same thing. Now, the way we calculate it is actually quite simple. So it's nice for elements because you can just go to the periodic table, look up the atomic mass, and that tells you the mass of 1 mole of that substance. For chemical compounds that have more than one element in the formula, it's pretty easy to get the analogous quantity, which is just to add together all the individual atomic masses that are in that formula. So there's a little bit of effort that goes into that. If we don't give you the molar mass of something, you have to calculate it yourself. But it's adding up the individual atomic masses from the chemical formula. So the chemical formula tells you all the elements that are present, and it also tells you how many of each of them are in that formula. So both of those together allow you to just add up all the contributions from the individual atoms and get a molar mass for the whole compound. So let's just start with an example of how we do this. So if we have glycine, which is the simplest amino acid, so later on when you take biochemistry, you'll learn all the amino acids most likely, and this is the simplest of them. So the formula for glycine is C2H5NO2, and we want to know what is the molar mass. So when you look at a chemical formula like this, there are sort of two ways of interpreting it. In the stuff that we sort of talked about in the first 4 chapters, we were doing everything at the atomic molecular level. So we would say, well, okay, one molecule of glycine has 2 carbon atoms, 5 hydrogen atoms, 1 nitrogen, and 2 oxygens. And that's not enough information to draw the structure, for example, but we would use that information at some level to figure out something about the molecule. But at this point, we're talking about moles, and the other alternative interpretation of chemical formulas is that if you have 1 mole of this substance with this chemical formula, the subscripts in the top chemical formula tell you how many moles of each element you have in 1 mole of that compound. So 1 mole of C2H5NO2 would have 2 moles of carbon because there's a subscript of 2 next to C, 5 moles of hydrogen, 1 mole of nitrogen, and 2 moles of oxygen. Right? And so then from there, we can calculate the molar mass by just, again, adding up all the individual atomic masses. So we have 2 moles of carbon, and the atomic mass of carbon, we have to look up all the atomic masses on the periodic table. So carbon, hydrogen, nitrogen, oxygen. They're all up here, mostly. Carbon is 12.01, nitrogen is 14.01, oxygen is 16.00, 2 decimal places is plenty. And then up here, hydrogen, 1.008. Okay, so those are the 4 that we need. I'm not going to flip back and forth 4 times, but you'll need all 4 of those atomic masses. And then you multiply those by the coefficients to get the contribution of each of those. So carbon has a coefficient of, or subscript of 2, so 12.01 grams per mole for carbon, plus 5 hydrogens in the formula times its atomic mass of 1.008, plus 1 mole of nitrogen in the formula, and its atomic mass is 14.01. Again, the individual atomic masses that I'm giving are all from the periodic table, and then multiplied by the subscript, and then 2 oxygens in the formula with an atomic mass of 16.00 for oxygen. I forgot to mention one thing earlier. If there was any confusion about this, why do I sometimes spell mole M-O-L-E and sometimes M-O-L? MOL is the abbreviation for mole. It's the world's stupidest abbreviation because it's 1 letter different and it's pronounced exactly the same. But MOL is the abbreviation for mole, which just has an E at the end. So don't get confused by that. But I'll typically write it as MOL, especially in conversion factors like this. And so then that's going to be, again, the contribution from carbon, hydrogen, nitrogen, and oxygen. And we just add all those together and get a molar mass of 75.07 grams per mole, which tells us that 1 mole of glycine would have a mass of 75.07 grams. So it's the same relationship, just comes from adding up all the atomic masses. All right, now sometimes, there's a little bit more to this. So we might ask you, what is the formula mass of a compound where we just give you the name? Now, if you're going to determine the molar mass or the formula mass of anything, you need the formula. And if we just give you the name, you have to be able to convert name to formula. So long story short, don't forget everything you've already learned. It will come up from time to time. So if we ask you for the formula mass of lead-4 sulfate, I guess I would have to have told you ideally that lead is Pb. That's too far down the periodic table for you to have to know that, but lead is the element that has the abbreviation Pb, but we need to get the correct formula if we're going to get the formula mass correct. So if we have lead-4, that means we have lead with a 4+ charge. And then sulfate, we have to remember, is the polyatomic ion that has the formula SO4 2-. So the exam only was a week ago, so hopefully you haven't forgotten all that already. And so we have lead 4 plus SO4 2-, which means the correct formula for lead sulfate would be Pb and then 2 SO4s. If you cross multiplied, you get Pb4 SO4, or sorry, Pb2 SO4 4, but this is the simplest formula for that. Lead with 2 sulfates to balance the charge. So that's the formula. We have to remember that this 2 outside means that there's 2 entire SO4 2- in there. So when we're counting the atoms, we have to make sure we do that correctly. So if we want to get the formula mass, then we have 1 lead in the formula. And the atomic mass for Pb, lead, is 207.20. So that's the atomic mass for lead. That's going to be the first number we need. And then this formula has a total of 2 sulfurs in it. Each sulfate has 1 sulfur, but there's 2 of them in the formula. So there's 2 sulfurs in the formula. The atomic mass for sulfur is 32.07. If you don't believe me, here it is, 32.07. Done these too many times. I don't have to look them up, but I don't expect you guys to be able to do that yet. So 32.07 is the atomic mass of sulfur. And then oxygen we just saw, which was 16. And in total, how many oxygen atoms are there? Well, there's 4 for each sulfate, 2 total sulfates in the formula, so a total of 8 oxygen atoms in this formula. 16.00 for oxygen, as we just saw. And so that number comes out to 399.34. So a rather larger number in this case. Write the units out. Don't forget to do that. 399.34 grams per mole. So same story, just a slightly more complicated formula and the additional step of converting the name into the formula, which we need to be able to do this. All right, pause for questions. Good. All right, and then the last example on this topic today. This is an example from my own research lab from a long time ago. So it's a compound that has iridium as the metal in there, but many other things too, and it glows red when you hold it up to a light source like that. Okay, so that's just a little fun background. But the important part of the problem is that this compound has a molar mass of 774.94 grams per mole. How many molecules are in a 1.00 gram sample? So a very similar problem to one we did earlier, just this time talking about molar mass of a compound instead of atomic mass of an element. And because it's a chemical compound, the mole relationships are going to tell you how many molecules are in that compound, not how many atoms, because each individual unit of that compound is a molecule, not an atom. All right, so the number of molecules that we would have, we can start with what we're looking for. Number of molecules, we write out what we're given. There's 1.00 grams of this compound. We don't know the exact formula, so I'm just going to write iridium in brackets because it has iridium in it, but we don't know the formula. We don't need it for this problem because we gave you the molar mass. We don't have to calculate that. We already have that number. So the first thing to do is convert to moles, as we said. And we want to find out how many molecules there are. So we're going to use Avogadro's number eventually, but we can't go directly from mass to that. So we have to convert to moles first. So we want the grams of compound to cancel and convert into the moles. The molar mass of 774.94 grams per mole tells us that there's 774.94 grams of this compound in 1 mole. So that tells us how many moles of compound we have. And then from there, it's once again just Avogadro's number, which we'll use a lot at the beginning of chapter 5, not so much after that, but we want to convert moles of compound into the molecules of that compound that we have, which again is Avogadro's number. 6.02 times 10 to the 23rd molecules in 1 mole of that compound. So moles cancels out. And that tells us how many molecules you would have, which is, again, quite a large number if we're counting individual atoms and molecules typically. 7.77 times 10 to the 20th molecules. All right, so another 2-step process, identical to what we did before. My text is getting messed up. Let me save that in case we're about to freeze. Kind of got messed up a little bit, not too bad. All right. So that's going to be, again, similar to what we did before. So molar mass, very analogous to atomic mass. One other slight offshoot, because I don't know if I have an example exactly like this. If we had asked you, it wouldn't be possible here because we didn't have the chemical formula, but if we'd asked you, for example, in lead sulfate, how many oxygen atoms are there in 1 mole? Again, you'd have to account for the fact that there's 8 oxygens in the formula. So the molar mass would tell you how many of this entire formula unit are in 1 mole, but the number of oxygen atoms would be 8 times that because of the 8 in the formula. So you'll see problems like that in the homework that often trip people up. So that's an additional step you can sometimes have. But the relationships are all kind of centralized around here that we gave. All right, so the next topic we're going to move to for the rest of today is going back into mass percent and how we relate this to the molecular formula. So we covered mass percent very early on in the semester. Again, I think it was the lecture that got canceled for the threat of ice, which never actually happened, but it was cold. So I guess we didn't want people from Houston to have to deal with cold weather, so we stayed home that day. But we covered mass percent back then, and it was on the very beginning of the course stuff that we did. So as a review, the mass percent of an element in a compound is how much of that element we have in the compound over the total mass of the compound itself, multiplied by 100. So we kind of defined that early on, and we did a lot of mass relationships early on. And now we're going to see how does this relate to then the molecular formula of the compound, which is not something that we covered at that point. So when you have a molecular formula, you can assume that you have 1 mole of that compound, because mass percent is an intrinsic quantity. It doesn't matter if you have one tiny fleck of that compound or a giant pile of that compound. The mass percent of the element will always be the same. It's intrinsic to that compound. It's not dependent on the amount of substance that you have. So if we want to relate the chemical formula to the mass percents of elements, we assume that we have 1 mole of compound. And then the mass percent is going to be the mass of that element in 1 mole divided by the molar mass of the compound, because molar mass is the mass of the entire compound that's in 1 mole. And then multiply by 100 to get it to a percent. And this numerator here, we'll do example problems so you'll see it. But this numerator is basically just the, when we're calculating the molar mass, it's just the contribution that comes from that individual element, which is, again, the number of moles of element in that compound multiplied by its atomic mass, and then divided by the entire molar mass for the whole compound. So going from formula to mass percent is pretty straightforward. So if we have the example of glycine that we did earlier, and we want to say, what is the mass percent of carbon in glycine? So each of these elements in glycine, all 4 of them, is going to have a certain percentage of the total mass that would make up that compound, and we can now calculate it for any or all of them using just the molecular formula and the molar mass. So if we assume that we have 1 mole of glycine with the formula of C2H5NO2, we calculated earlier that the molar mass of glycine is 75.07 grams per mole. So that means 1 mole of that compound would have a mass of 75.07 grams. Okay. So that's the mass of 1 mole. How much carbon is that in that 1 mole of compound? Well, we have the mass of carbon is, in the chemical formula, we have 2 moles of carbon, a subscript of 2. The atomic mass for carbon, as we gave earlier, I don't want to flip back and forth too many times, but it's 12.01 for carbon straight off the periodic table. So there's 12.01 grams of carbon in 1 mole. And that comes out then to 24.02. So of this 75.07 grams, that corresponds to 1 mole of glycine, 24.02 of that is carbon, because there's 2 moles of carbon in the formula, and that's the atomic mass of carbon, which is the amount each mole would have. So now we have all the information we need to calculate mass percent. It's just those two divided by each other multiplied by 100. So there's 24.02 grams of carbon in 1 mole. The mass of 1 mole of compound is 75.07 grams. Multiplied by 100, and so we get 32% exactly for the mass percent of carbon. And so you could do this for all 4 of the elements, and if you add them all together, they should be 100. And you do it the same way. You figure out the contribution of that element to the total mass based on the chemical formula and the atomic mass of that element, and then divide it by the entire molar mass. So that's pretty straightforward. If we give you the chemical formula, you can go to mass percent. Now, the way that's more interesting and probably going to be coming up more often on tests, which we'll cover next time. Gosh, we went through that fast today. You guys just don't have any questions, so I never. That's okay. You guys don't seem to mind when I'm done early. But just as a preview of what's coming next, what we're going to learn how to do next time at the start is go backwards. So here we took the formula, converted it to mass percents, which we can do for any element in the compound. But instead, if we gave you the mass percents of all the elements in the compound, how would you convert that to a chemical formula? So it's working backwards from here, still uses the same relationships, as we'll see. And so we'll cover that at the start of next time and move on to some other things related to mold as well. All right, so thank you for listening. I have plenty of time for questions afterwards if you have any, and I'll see you guys next week.